and Benjamin will be discussing today how to connect traditional beyond mean field methods or theories in nuclear structure with the new developments of ab initio nuclear structure. All right, so take it away, Benjamin.
Thank you very much for the introduction. So indeed, I will try to explain what is actually, let's say, the core of the Marie Curie grant that I received, and that is to connect beyond mean field calculation as we used to do it, for example, in Madrid or in Bordeaux, to ab initio nuclear physics. I mean, it's actually one of the parts of this grant. So first of all, because Arnaud told me that you have a group that is diverse, people coming from different fields, I will start with a general introduction. I will try not to be too technical because some people come to hadronic physics or atomic physics. I don't want to lose them into explaining all the details. But first of all, I will define what we mean by ab initio nuclear physics. So the main principle is that we try to describe the structure of the nucleus through considering first as a correct degree of freedom structureless nucleons, so Z protons and N neutrons, and to build the interaction between them from first principle. The golden standard nowadays is called chiral EFT, and these nucleons then interact, exchanging pions and also through contact terms. And then when you have this, you can try to solve as exactly as possible the Schrödinger equation, and using usually methods that can be improved towards the exact solution in a systematic manner. And one of the crucial point of nuclear structure in the last, let's say, 20 years is the immense progress in ab initio techniques. In particular, the reach of ab initio method has increased quite a lot compared to, let's say, 10 years ago, when the method used allowed to describe only the lightest nuclei or nuclei close to the shell closure, here represented by the line, the dashed line. But people have developed new methods since then, in the last 15 years, let's say, to methods that have much better scalings in terms of model space or the number of nucleons considered, to methods such as, for example, couplet cluster or self-constant Green's function that you have may heard in other contexts, MSRG, that is more nuclear physics in a sense. And thanks to this method, it has been possible to push the reach of nuclear ab initio method up to medium mass nuclei, and some nuclei that can be considered as maybe heavy, around like 100 nucleons, although it's still medium mass in a sense. So people have developed a new method, like the one I described, and more recently, people have also tried to build, so let's say, hybrid method, I will say, like what is called valence space MSRG. That is a method that basically, if you have heard about the traditional shell model calculation in nuclear physics, I guess in Barcelona you have Javier Hernandez, so maybe you have heard of that. It's basically a way to build a shell model from first principle, where thanks to this IMSRG method, you build an Hamiltonian that is adapted to a given valence space, and then you perform exact diagonalization in this valence space. And so, as I said, great progress, although it has to be contrasted by the fact that not all methods can reach all nuclei in this chart. In particular, I guess most of the blue points here were actually calculated through this valence space IMSRG. And not all methods can compute all observables for each nucleus. So great progress, but the nuclear chart is actually much bigger. So here I represent a much more zoom out version, if you want, of the nuclear chart. In red, you have all the ab initio calculation I showed before. In yellow, you have all the nuclei we know that have been evaluated, at least in the atomic mass evaluation of 2020. And in blue, you have all the nuclei that have been predicted using an energy density functional calculation, in particular, in this case, the GONID1M functional. So it is interesting to zoom out, because we realize that although great progress has been made, we still have a long road ahead of us, right? And in particular, if you realize that here you have nuclei with 300 or 400 nucleons. And also, it's not only about the number of nucleons, but also the structure of the nuclei we want to describe. Here, I represent the average axial deformation of a mean field calculation, still using this GONID1M functional. And in red, you have all the nuclei that are called prolate, that is, that are elongated along the symmetry axis. And in blue, you have all the nuclei that are oblate, that is, are squashed or compressed along the symmetry axis. And you see that as soon as you move away from the magic numbers, we are still represented by this line, these numbers, nuclei tend to be deformed, right? At the magic numbers, they tend to be spherical in gray. And as you move away, when you are in the middle of a shell, for example, here, you are very deformed. And it's something you have to take into account when you build your method. So that's why one of the ideas is to reuse all the knowledge we had in, for example, in mean field calculation, in energy density functional calculation, and people have done the same in shell model calculation with valence space and MSRG, to reuse the method we used in the past, but now trying to connect them to the ab initio nuclear physics. In my case, I will describe how we can try to connect the projected generator connect method that we'll explain in a few minutes to the ab initio nuclear physics. And this method is very nice because it's a method that is very powerful, that has been used for decades with energy density functional. And it is very nice because it allows to include very efficiently static correlation, such as deformation and pairing, which are very important in the description of nuclear structure. Also, it's a method that we explain now respect the symmetry of the Hamiltonian, and that can access all the the full nuclear spectroscopy, excited states, and compute various, all basically the necessary, the interesting nuclear structure observables, and decay also, observer for decay. And so the thing is, so how do we connect this projected generator current method to ab initio nuclear physics? So the first thing that we can do, the most basic one, is just to take this method, such as it was designed originally, and to use, instead of an energy density functional input for the Hamiltonian, to use basically just a chiral EFT matrix elements in your PGCM method, in your PGCM calculation, and see what comes out. And I will show that it's already can be used to do some physics with that. And but that's only, let's say, the first step of what we can do. Basically, it can be considered as the first order, or the order zero of your approximation. In such, similarly to, for example, if you consider methods such as many-body perturbation theory or couplet cluster, at the order zero, you have HFB or Hartree-Fock calculations, and then you build on top of it more correlations. And you can do the same thing, but instead considering a much more correlated wave function, that is the wave function you obtain through PGCM calculations. In particular, I will show how to include what we call dynamical correlations through what has been called the in-medium generator current method, that is a merging of the MSRG method with the GCM. But you could, you could design some other schemes if, depending of what you can do, or what you want to do, or yeah, we'll keep it at that. And so first, what is exactly the projector generator primary method? So it is a method that was initially proposed in the context of fission by Hill, Griffin, and the famous John Archibald Wheeler, that is better known for his work on black holes and general relativity. And so the idea is simple: it is to consider a variational ansatz that is a linear superposition of many states that vary, that depends on a continuous variables Q, that can be a single variable or a set of continuous variables, and to consider this linear superposition as your trial wave function. And then what you can do is just to minimize the expectation value of the Hamiltonian for this trial wave function. This is called the Wheeler-Griffin equations, and through that you determine the optimal weight F for your states, where the psi here are, I will explain what are the psi in a few minutes, but they are kept fixed. So typically in nuclear structure, many calculations have been performed using as continuous variables the quadrupole deformation, that is the most common one. Some people also use pairing, or for example in Madrid, people also have used octupole deformations. You could, or in principle, add other things like the radii and so forth. Another interesting thing is that in practice, because we solve numerically all of those equations, we discretize the generator method. That is, instead of taking actually real continuous variables, we take discrete values for the Q, or for the set of variables. So you have a sum that is like that, with just superposition, and solving the variational principle is equivalent to diagonalizing or solving the generalized eigenvalue problem, where you have to fully diagonalize the Hamiltonian and the norm at the same time, because there is a priori no reason for the different state psi to be orthogonal. So it's an additional complexity you have to deal with. You have to diagonalize the norm at the same time as Hamilton. And in a sense, if you want to view the things from a more general perspective, if you accept this, like I said, this sum, like you as a general ansatz rather than the pure continuous integral, you can think of the generator method as a diagonalization of the Hamiltonian in a certain subspace spanned by a set of possibly non-orthogonal states that you selected according to their physical relevance. And that is a difference compared to, for example, traditional shell model, where you diagonalize exactly your Hamiltonian in considering in a basis where the states are, for example, Slater determinants. Here, basically, what you want to do is build much better basis states that contain much more physics, such that you can diagonalize in a much more restricted space and still get a nice result. So you put more emphasis on building a set of basis states or that contain more physics. So so the question then is, what do we take for the state psi? So first, I will consider Bogoliubov quasi-particle states that I label phi. If you don't know what it is, it's just a generalization of Slater determinants that we use to include pairing correlations in a simple way in our calculations. And so what we do first is that we perform several minimization. So we perform R3-Fock or R3-Fock-Bogoliubov minimization under constraints. Here I generically call the constraint operator Q, that depends on, let's say, the variable Q I, and I change this QI and perform several minimizations. I can also change even the constraint operator. And in such a way, I build many, many states. And the idea, if you want, is that it's not only the minimum that is interesting when you do this for the mixing. It's not only, for example, the lowest state with and its deformation, but you may want to explore deformation around the minimum, to explore the surface around the minimum. So that is a way to build many, many quadrupole states that contain different physics. But a disadvantage, in a sense, is that these states, for example, if depending on the constraint operator you consider, they may break the symmetry of the Hamiltonian. For example, if you use a constraint on the deformation, you will break the rotational invariance. That is, your states will lose good quantum numbers related to to the angular momentum. If you consider states that break to include pairing, we consider quadripartite state, but as a result, they break the particle number invariance and such that your state at the end do not have good number of protons and protons. And in another example is octuple deformation, where you break here the parity invariance, so your state do not have a good parity. So it's a thing we do because it's a very efficient way to include this kind of static correlations. So to go beyond this thing, we have to do what we call symmetry projected HRD. So I'm not going to describe in detail because it will take a while. If you want to have this article here that were recently published with Michael, and so this is a method that allow you to build states that have good symmetry properties. In addition to that, you will gain, usually it's not necessary, but it's really, it's usually the case, you will gain some correlation energy. And because you have the good quantum numbers, you can compute, you recover the selection rule for transitions and for any observable, actually. So just to say 2 more words about it. So basically how it works is that you build your state phi during the minimization, and because it does not have the good quantum numbers, it can be written as such a superposition where you have different state psi that have good quantum numbers, and this state is just a superposition. And what you do is that you use what's called projection operators that are given to you by group theory, and you apply them to your state phi. You will obtain, depending on phi, either one state or a set of states. And if you rediagonalize H within this set, you obtain the components you want. And these are the states you will use in your projected GCM when you will mix the state through the Elliott-Griffin equation. And this is also what basically is represented here schematically. So here is an example of calculation of very preliminary calculation that we performed with Thomas and collaborators, just to show that what we could do. So it used a current interaction that contained a two body part and a 3 body part that comes from TU Darmstadt. Don't ask me too many questions because I don't know exactly what is in the interaction. At the time, I just use the matrix elements, but I don't know all the details of what is inside the interaction actually. And so the 3 body part here is taken into account through what we call the in-medium 2-body approximation. That is a method that we recently proposed in this archive draft, and that was also recently accepted in European Physical Journal A. So it should appear in a few weeks or a few days. And so what you do then is that you use this current interaction, you perform this minimization. Here, I consider 2 degrees of freedom, the deformation beta for axial, for the elongation, let's say, and the triaxial angle gamma. And so here in this axis, you have prolate deformation. In this axis, you have oblate deformation, and in the middle, you have all the deformation in between. So this calculation was performed in a model space containing 7 harmonic oscillator share with h bar omega equal 20. It is a slightly more complicated calculation compared to what I just described, because we did what we call variation after projection on a particle number. That is, we basically varied Bogoliubov quasi-particle. We included the symmetry projection inside the variation of your quasi-particle state. But as a restriction, I conserved good parity and also time reversal, because it makes things simpler. And at the time, I wanted just to have some results to see what comes out. So a few remarks in order. When first, here the minimum is oblate, but you can see that the surface is extremely soft against gamma deformation. So when you project, then it will not be the minimum anymore, actually. Second thing is that you see that the energies are extremely small compared to, I think, the experimental value for the mass is 110 of MeV, something like that for carbon test. So you are half the mass, experimental mass of carbon. So, well, in a principle, there is no reason for this Hamiltonian to reproduce exactly the mass of carbon 16, but it should be much closer than 50 MeV. And it's because when you stay at the mean field, or even VAP level, you miss a lot of correlations, such that this kind of absolute observable can be very far away from the experimental values. But it might be that the relative properties, and you see, for example, the deformation can be relatively well described. And also, I would like to stress that for me, it's very interesting to do this kind of calculation, because this kind of energy surface has been plotted for a long time in energy density functional calculations using very phenomenological functionals. And nowadays, we can do the same kind, we can do exactly the same kind of calculations, but using a proper Hamiltonian coming from first principle. And that's, in a sense, very interesting to see and to do, in particular for me, coming from more EDF background. So then the next step is to take certain points in this surface. Here I selected point with a delta in beta of 0.2. So I selected 15 states in this surface, and I perform the symmetry projection and the mixing. And here I compare to experimental results. In particular, some people at Ganil performed recently new experimental runs concerning carbon 16. And it was what motivated this preliminary work. And so you can see that already with 15 states, you reproduce quite well some of the states. You don't have all the states, but in a sense, I only added 15 states. I still have time reversal and good parity, so I miss certain states for sure. And if I consider more general than that, I think I could get a much better agreement for the 0 plus, that is, I guess, somewhere higher in energy in this spectra. But already, you see that with a simple PGCM calculation using a chiral interaction, you can say something. I'm not even sure honestly, I'm not even sure the best couplet cluster or whatever calculation could perform a much better spectrum than that. So I think it's a very interesting method to describe this kind of physics. So to perform this kind of calculations, we developed at Madrid. So it's a project that started in Madrid, first year when I was there, and now is funded by a Marie Curie fellowship. We have started to develop a new numerical suite that we call Taurus, I mean, you pronounce it how you want, in French or in Spanish, and or in Latin, it will be more correct. But And so it's a numerical suite that allows you to perform very general symmetry projected variational calculations. It's made of 3 main programs. The first one is called VAP, which allows you to perform variational calculations, such basically to perform this kind of calculation here. That was already published earlier this year, so you can download it on this GitHub repository. And 2 other codes that I'm currently finishing, the Taos PAV, which can allows you to perform multiple symmetry projections, and Taos HWG that solves the linear equation. So basically, the first code allows you to perform this kind of calculation, and if you combine with the 2 other codes, you transfer from this side to this side. And this one, I hope that will be published soon. Hopefully, I mean, if I have time, if I don't have to give too many seminars or things, I should be able to finish them before the end of the summer. I mean, basically, this code is finished, and this one is just a matter of cleaning the code. In addition to that, we also provide some smaller script and code, for example, to convert the interaction in a format that can be read. For example, that can be read by Taos. For example, we added a script to convert from the format of Boccadorata, which is another ab initio code that was of Cario Barbieri, that is also public, and to convert from this format to the one, because it's also something that is important when you want to use interaction. Is very usually everybody has its own format, and it can be a pain in the ass to get Would it be possible to mute Bruno Julia? Because I can hear him. It's just I don't know if it's possible to mute. Thanks. So certain, just the main feature of the code. I'm not going to describe obviously all the routines, obviously, but just a few key characteristics of the code. So first, it's code written in Fortran. I'll say 2008 because some of the commands are in 2008, although most of the code could be, I guess, compatible with 90 or 95, but there are some specific things that I use that are from 03 or 08. So the code that can be that include parameterization. You can combine OpenMP and MPI at the same time, and you have also different degree of MPI parameterization if you want to focus on the for example, to speed the code in terms of CPU time, or if your program is more memory side, you have different type of MPI parameterization. The code works in a spherical harmonic oscillator basis. That is the usual stuff, textbook spherical harmonic oscillator basis. We consider all the states of a given angular momentum of the substates, and we consider also a space that is invariant under isospin rotation. That is, we consider same levels for protons and neutrons. But apart from that, no model space is assumed. That is, you can perform a no-core calculation or valence space calculation. You just feed basically the model space to your code, and it will perform the calculation. We also do not assume any shape for Hamiltonian. The only restriction is that we can at maximum consider 0 body, 1 body, and 2 body terms. So no full 3 body terms. And with that, we can perform calculation using matrix element coming from Carol EFT, or using shell model interaction, such as the one used, for example, in the code Antoine. Actually, the code is built in such a way that an Antoine interaction, I mean, it can read natively interaction in the Antoine format of the famous shell model code Antoine. The 3 body can be included, but only through normal order 2 body approximation or something similar, such as the paper I mentioned before. For the Bogoliov quasi-particle states, we consider very general quasi-particle states. That is, the only restriction is that they are real. But apart from that, you have no symmetry restriction. So it's up to you. You have certain options to start from a state that is spherical or axial, or that has good parity, but in the most general case, you can consider a real general probability of particles without any symmetry. The code allows you to perform different kinds of minimization. You can do VAP, PNP, HFB. You can add constraint or do fully unconstrained calculation. There are many possibilities for the constraint. You can add quadrupole, octuple, hexadecapole, and so forth. I mean, and pairing and other things. And for the symmetry projection part that is not yet public, you can basically project on all important quantum numbers. The only one missing is isospin. There is a version that does that, but it will not be in the first public version of the code. So, and if you want to use it, I mean, you just have to go to the repository and you can download it very easily. So next, I will try to show you the next step of what we can do in terms of connecting GCM approach to ab initio nuclear physics. So it's something that I collaborated with people when I was in the United States, with people from Chapel and Michigan State University, and the goal was to combine two approach, the PGCM and so the one method I described with the MSRG, that is one of the specialty of people at Michigan State University. And the two methods are very successful, but they can be combined to obtain something even better, or at least something that can be used for certain physics better. So the idea is to use the PGCM to include what are the static correlations in your wave function, so the deformation, the pairing, and it's also, as I said, it's a method also that has the advantage of respecting the symmetry of H if you do quantum number projection. And then when you can also use to include dynamic correlations that are difficult to take into account in the PGCM framework to use the MSRG. That is, by dynamical correlation, we, let's say, speak about few particle excitation on top of your functions. And the advantage of MSRG is that it can include these dynamical correlations. It is a method that is systematically improvable towards the exact solution, contrarily to the PGCM. The PGCM is variational, so in a principle, you could converge towards the exact solution, but it will be extremely inefficient and it's not very controlled way. You don't exactly know what you're missing sometimes. So either you consider the full space in your ansatz, but basically you have a very inefficient diagonalization. So it's much better to use this kind of control proper ab initio method to build towards the exact solution. And the goal is that by combining these two methods, we can try to keep the MSRG at low order. That is, here MSRG2 was considered, maybe MSRG3 later, because all these ab initio methods, although they can in principle give you the exact solution, if you have to go to the 10th order, I mean, you're dead from numerical reasons. So yeah, in principle, they can convert to the exact solution, but it's better if you can do it at low order. And that's the basic idea, again, is to use a much better reference state to build on top of it your correlations. So if you don't know MSRG, I'm just going to explain very rapidly because it's going to be too technical, and I'm not even the biggest expert in the method. So the principle is that if you start with your Hamiltonian, H0, you can transform it through a series of unitary transformations that are parameterized by a continuous variable S here, and to use this unitary transformation and evolve your S toward infinity such that you block diagonalize your Hamiltonian for a given reference state. So to evolve and to obtain this unitary transformation, you have to solve what is called a flow equation. I'm not going to enter details, but it just says that in case you remember and connect to something you already know. And also, one thing is important, when you have evolved, when you obtain your unitary transformation, you need not only to transform your Hamiltonian, but any observable that you're interested in. Few remarks. Well, here, as I said, we consider what is called the MSRG2, so which is called the normal order to body approximation for the MSRG. And one thing that is very interesting about this method is that when you build this kind of by evolution and by creating this different Hamiltonian, you can then reinject them in other series. It's what we do in the EMGCM and what people do also in valence space MSRG. I think that is a very nice thing about this approach, this capacity of building evolved Hamiltonians that can be used with whatever other method you can think of. And so here you have a schematic representation how it works. So if you start with your Hamiltonian at S equal to 0, and if I call 0 particle 0 all my reference state, and here I represent the matrix of the Hamiltonian for the different particle excitation on top of my reference state. If I start with this matrix and I evolved, I will uncouple here in white. The matrix elements are 0. I will uncouple my reference state from all the excitations. And in principle, if you evolve toward infinity, your 0 particle 0, your reference state, the expectation value of your reference state, will be the exact ground state of your Hamiltonian. It's also that's one of the very nice features of this method. And so how it works in practice. So first, what we do is that we start with let's say the bare Hamiltonian H0. We perform a PGM calculation, such as the one I've shown previously. It gives you a PGCM wave function that you use as a reference state to build your evolution, your IMSRG evolution, such that you obtain your transformation. And then when you have your transformation, you have your evolved Hamiltonian, and you use your new evolved Hamiltonian in a new PGCM calculation. The advantage of doing a second PGCM calculation in particular is that PGCM, well, you rediagonalize a little bit your Hamiltonian, so things you are missing, and also you have access easily to all the spectrum and transition through the PGCM. In principle, you could loop and say, okay, I've done a PGM calculation with my evolved Hamiltonian. Why not just evolving again? In principle, you could do it. I don't think it was done. Until now, because in principle, it's not really needed, and it had another complexity. But it's something that people maybe at some point try to do. Who knows? There is an additional complexity here because we, as I mentioned in the abstract of my seminar, I want to talk about neutrinoless tuple beta decay, and in that case, you have to consider not only one nucleus, which is the initial nucleus, but also a final nucleus that has different number of protons and neutrons. So, in principle, what you could do is to perform PGCM and plus IMSRG calculation for the first one, and then for the second one, and try to combine the unitary transformation that are different, that will be different in that case. But it's very complicated because you can't use simple formula to combine the two unitary transformations. So instead of that, we do a PGM calculation for the initial and final nucleus, and we use an ensemble reference in the evolution to obtain the unitary transformation. And we checked that in particular, it did not the weight of each of the initial and final state did not change the results. And it's a very simple way to bypass this problem of having two different nuclei. So we used this method to make some calculation about neutrinoless beta decay, in particular the nuclear matrix element. That is an important thing from a nuclear structure point of view. So if you don't know about it, I guess you know, you have people also, I guess, in Barcelona who work on that. So, but I will just recall, and also I remember there was a talk a few weeks ago about it, so I will be fast, but it's a decay that where a nucleus transition from Z proton to Z plus 2 protons and losing 2 neutrons in the process. There is what is called the two neutrino double beta decay, where in addition to this transition, you have 2 electrons and 2 neutrinos. It's a transition that is allowed by the standard model that has been observed, I think, for 10, 15 isotopes. And that is very interesting. It is the slowest process that was ever observed by man. So, I mean, if you want, I mean, something nice, if you want to advertise the interest, I mean, why nuclear physics is important, you can use this kind of very rare process to say, look, we can do things that are more interesting. I mean, it's not what I think, but to sell it to the people, to the people in the committee. And also an important fact is that so to have a chance to observe this double beta decay, you need the single beta decay to be forbidden, because the process is so much faster. You will have never experimentally no chance to observe the double beta decay. And then there is a more interesting one, the neutronous double beta decay that has never been observed, where you don't have these 2 neutrinos in the decay. And this is, in that case, it will mean that the neutrino is its own antiparticle, that is, it is a majorana particle. In that case, it is a process that is forbidden by the standard model. We have not observed yet the process, but the current experimental lower limit for the half-life is 10 to the 25th, 26th year. So people are actually, there's a lot of experiments around the world trying to observe this limit, because obviously if you get that, I guess you will get a few years later a Nobel Prize. So a lot of people are interested in that in the US. I think there is an experiment in Spain, like next, I think, that is, I may be wrong, but I think it is this one. And here, the interesting part for nuclear physics is that if you consider the lifetime, or here the inverse of the lifetime, it can be written like this. I'm not going to describe every single part of the equation, but two important parts, two unknown, that are what is called the effective majorana mass, that depends on the neutrino masses that are unknown nowadays. And we only know the difference of the square of the matrix of the masses, but we don't know the masses themselves. And the nuclear matrix element in red, that is something that cannot be measured and that has to be computed from using nuclear theory. So it's where we enter in the game. One comment, though, is that this half-life is under the hypothesis that basically you have 3 light majorana neutrinos that are the neutrino we know of that dominate the neutrino-less double beta decay, because you could imagine more heavier particles or other processes, and so there is an assumption behind this formula. And the goal is that if we can compute M, we can evaluate, give certain range of expectation values for the half-lives given M beta beta. We don't know M beta beta, but we can, there are certain range that we can evaluate. And the other possibility is that if we know M beta beta, and if someone happened to observe neutrino-less beta decay, double beta decay, we can access M beta beta. We can constrain it further. So that's one of the interesting part of where nuclear physics can shine in this game. And so the thing is, people have computed nuclear matrix elements for a long time. Here you have people in Spain, for example, here Thomas in Madrid using energy density functional. But all the method that has been used, and people also using the shell model, obviously, and people one of the problems is that all the methods, shell model, QRP, ADF, are all in a sense phenomenological, and they have a strong disagreement. You can see it on this graph, where courtesy of Jonathan Engel, where you plot all the half-lives for the different methods, for the different candidates, which are represented by the number of nucleons. And you see you have a wide spread. You have something like factor of 3, which corresponds to roughly a factor of 10 for your lifetime. And the problem is how to discriminate between all these matrix elements, and are any of them correct anyway? I mean, we have no idea how to improve, in a sense, what is missing in a given model. And here, I think personally that is one of the advantage of ab initio calculation is that it is less, it relies less on phenomenological assumptions, so you can hope, at least, and it's a hope, that you can perform more constrained calculation, or things you can really, you have more chance to pinpoint the real value through this kind of calculation, although it has to be demonstrated. But one of the advantages in particular is that through chiral effective field theory, both for Hamiltonian but also for the transition operator, you can hope to progress in the right direction. And so we perform calculations for the lightest interesting candidate, that is calcium-48. There is an experiment existing. It's what I'm saying is the interesting candidate, because you will see a lot of people, in particular ab initio, compute neutrinoless double beta decay for very light nuclei where there is no chance of observing them. I mean, it's calculations that are useful to benchmark the method, but they have no interest from an experimental point of view. So here there is an experimental program, at least one, maybe one other one, I don't remember, that is called candles. And the advantage of this candidate is that it has a very large Q beta beta that is above all the backgrounds, such that you can hope to have a better signal. The big problems is that the calcium-48 is very low isotopic abundance, so you cannot build large-scale experiments with that. And actually, calcium-48 is not, it is the lightest one that where there is an experimental program, but the real lightest one that is interesting should be the germanium-76. So calcium-48, in a sense, is interesting, but not the most interesting. And so we perform calculation in different model spaces with 7 oscillator shell, 9 and 11 oscillator shell, with a cutoff for the 3-body at 3 max equal 14. We use the famous Anthem and Marlight interaction for the chiral interaction with the 2-body and 3-body parts. We consider two types for the 2-body. Although I'm not going to talk about this one in the results. And we use our MSRG2. And in this first calculation, we consider the projected GCM exploring only the axial deformation. Calcium-48 being spherical and calcium and titanium-48 being very, I mean, can be described quite correctly using the axial deformation. It was not necessary to go to include triaxial deformation, which make the calculation much more complicated. So here are the results for the calculation to explore here for this EM 1.82.0, 2 possible value of H bar omega for 3 different value of Emax in each case, and it was so we obtained fitting an exponential, decreasing exponential in both cases using Bayesian inference methods, and assuming that they should get the same results in infinite model space, we obtain the value of 0.61 with an uncertainty for the Bayesian inference for the fits. Although I have to say that this assumption that you have a decay, decreasing exponential is it itself, I mean, there is no justification behind it. I mean, it's something we observe empirically, but there is no reason I can think of, or maybe I'm wrong, but to say that you should have this. But it's something that seems to work very well, at least in practice. So we obtain this value that has been published in Physical Review later last year. And to finish, we can compare this value with the other method for this nucleus. So you have a lot of older calculation using phenomenological interaction. For example, here one of Thomas with Bonny. And also, more recently, people have done this same calculation through the valence space MSRG, so people of Triumph. And they obtain a value which is, I think, 0.57 or something like that. So this is in agreement with our calculations using the same interaction. They used a slightly larger model space with 13 oscillator shells. And you see that these two ab initio calculations tend to be smaller than all this other empirical. And in this paper, they observed the same thing, if I remember correctly, for germanium 76, and the other one was tellurium 130. No, maybe no, it was selenium 82. And so it's nice to see that the two methods agree very well. That is also one of the advantage of initial calculation. You can compare them directly using Symmetry. There is a caveat here, is that recently people realized that there was a missing leading order term in the KRLFT for the neutrinoless transition operator. So in that sense, this is not the final answer. It will need to properly calculate this new leading order term, and in particular to fit the low energy coefficient associated with this leading order term. And I don't know if they have understood how to do it yet. Obviously, the best way would be through lattice QCD, but it's not possible. People are working on that direction, but it's not yet possible, I think. And so yeah, it is to be taken with a grain of salt, because without a leading order term, maybe it will change a little bit. But at least it's nice to see that the two methods agree. There is also a calculation with a deformed coupled cluster that gives something smaller. I mean, maybe I mean they have a large uncertainty, but it's at least in this range of matrix element, and very much smaller than all the empirical, the phenomenological interaction. And so I think I will stop there. So in the future, I think the immediate future will be, I think, the release of the two other codes to have the full numerical suite free and on the GitHub repository. I guess it could be done like in a few weeks if I can focus on that. Also, to use the PGCM calculation to perform the spectroscopy calculation on light nuclei, for example, carbon cells, but I mean, we can imagine many other cases. And also, I did not want to talk about it because it's already very a lot of things to talk about, but this code can be also used to perform phenomenological valence space interaction calculation with phenomenological valence space interactions, such as the one used in the traditional shell model. And if you want to, you can invite Thomas or Adrian, his PhD student, to talk about that. They are doing some calculation with this code. And finally, all the people, I just put a slide with all the people I worked with on this topic or before, that are entitled the Nuclear Physics Super League. Also, I hope it will last longer than the European Super League. And yeah, so thank you very much for the talk, for listening to.
Thank you, Benjamin, for